Hello everyone. So in this video I'm just going to give you some hints on how to solve the quiz 2 questions. So the first two questions are regarding the what do we call ideal gas equations. Okay, so in the formula sheet I'm just going to show you in the middle section we have quite a few ideal gas equations listed here, but the most common ones we're going to use is that the first one is PV is equal to MRT. Okay, so the only thing in here is that we know this is pressure, volume, mass, temperature. Okay, so this is R. R is called a specific gas constant, and R is calculated by using this equation. So R0 divided by M. Okay, so be careful, this is capital M, so it's not that M. This is mass, and this is the molar mass of a specific gas. So depending on different gas has different molar mass here. But R0 is what we call the universal gas constant. So that's a constant. They've got a subscript of R0 here. Okay, so basically we're just going to use these two equations. Now I'm going to copy these equations down. PV is equal to MRT. Okay, and R is equal to R0 divided by M. As I said, R0 is a constant there. So there's a very common mistake here, so I'm just going to write a unit. So you can see that most mistakes are made regarding the units. So there's 32 here, molar mass of oxygen, okay, kilogram per kilomole. Okay, so if we put the units behind all the values, so you can double check the final unit. Okay, so we have kilomole here. These two will be deleted. Okay, so the final answer will be that with the unit. Be careful about the unit is kilojoule. Okay, kilojoule per kilogram K. Okay, so you need to pay special attention here because this is a kilojoule. So bear in mind, kilojoule is not SI-based unit. So now we're going to use that. Okay, so in this case, we can know that V, P, T, all these have been given, but they're in probably different units, probably not SI-based units. So what we need to do is that when we do the calculation, we need to convert that to SI-based units, everything to SI unit. Now we need to calculate the mass. Okay, in this equation, if we're going to calculate the mass, then we can divide RT on both sides, so you have mass left on the left hand side. And so that's PV divided by RT. So you can see here we have 1, 2, 3, 4. Okay, four variables, so we need to convert everything to SI-based unit. P, so that's 261 bar. Okay, so times 10 to the power 5 to Pascal. V, 92. So that's liters. So we need to convert that to cubic meter, because 1 cubic meter is 1,000 liters. Okay. R here, we just calculate R. Right. But as I said, this is a kilojoule. So we need the times 1,000. Okay, this bit is I think a very common mistake, times T, and also again need to be careful because this is centidegree. So you need to add that 273, right? So now we can make sure that everything now is in SI-based unit, so that the final answer must be SI unit for M as well, which is a kilogram. Okay, so in the right unit in the kilogram here. So you just do this big calculation, which gives you the answer of 60.3 kilogram. So that's the answer for the first one. Okay, so let's move to the question 2 here. Question 2. So it says a rigid tank. Rigid tank means that the tank can, the volume inside the tank will be the same and also this has been confirmed here. Isometric process means that the volume is kept constant during this process. Okay, and we know P1, T1, and we're going to calculate. We also know P2. We're just going to calculate the T2. Okay, T2. So someone may think that the variables given are not enough to calculate the T2, but I will show you actually they are enough. Okay, so we know that ideal gas equation, right? So that's called PV is equal to mRT, right? So PV and the T, so all these properties, okay, are changing during the process. However, for a closed system, the mass is fixed, okay? R for a specific gas. Once the gas, such as oxygen or air or whatever, if it's in a closed system, then R is also constant. So actually you can move. You can divide T over there, okay? So this will give you PV divided by T is equal to mR. As I said, these two are constant, so then if you multiply them together, this will also give you a constant value. So this applies to ideal gas in any process. Okay, actually I have already included that equation in the formula sheet. You can see, okay, PV divided by T is equal to constant, depending on different process P1 or P1 or 2, state 1 or state 2. Okay, so we can, as I said, we can write P1 V1 divided by T1 equal to P2 V2 divided by T2. Okay, as I said, this process is isometric. Isometric means that V1 is equal to V2. So these two has been cancelled each other. Okay, so now the equation left is actually a very easy equation. So you can use that to calculate T2. T2 is equal to this one times that one divided by that one. So it's P2. Okay, so P2 is 32 bar. T1. So this is already in Kelvin now. Okay, so you don't have to do any conversion. P1, 43. Okay, and this will give you the answer. Kelvin. In Kelvin temperature, in the unit of Kelvin. So just double check if the unit is correct. So that's it. That's it for question 2. And for question 3. So from question 3, we're going to solve some questions regarding the properties of the water and the steam. So when I say use a steam table, okay, so what I mean is that that's this booklet. Okay, so as I already stated in the announcement, so we have to use that, okay, because I said different versions, if you find on the website, on the internet, they actually give you different values. So this is not easy for me to mark, so we have to stick on this booklet. Okay, this booklet, and also I have uploaded a PDF version on Canvas, so you need to find out, you have to use this version. So steam table, so now we're going to use a steam table to find all these values. The first one, the saturation temperature of water at 70 kilopascal. So if you have a look at the steam table, you can see that all these pressures, okay, all these pressures in the unit of a bar. So you have to convert that to kilopascal, okay, to bar, right? So 1 kilopascal is 10 to the power 3, okay, so that's 70 kilopascal. Okay, and if you want to convert that to bar, you have to divide it by 10 to the power of 5, okay, because this is a 1 bar, right? So actually this one divided by that, you actually divide it by 100, so 70 divided by 100 give you 0.7 bar. So you need to use that 0.7 bar. So now the pressure is 1 bar, so it's previous page. Okay, here 0.7 bar there. So this column is called saturation temperature, so it's 19.0. Okay, so put 90.0, or somebody put 90, so both of them are correct. So this is the first one. The second, specific enthalpy. Okay, so we use what symbol do we use for enthalpy? So that's H. Okay, and saturated steam. So we have saturated water and saturated steam, and then we use the subscript G for saturated steam. Okay, and then we use F for saturated water. So that's Hg actually at the pressure over here. So megapascal. Megapascal is 1 million Pascal, which is 10 to the power of 6. So that's 1 megapascal is 10 bar. Okay, so this gives you that 15 bar. So 15 bar. Let me check the steam table. Okay, here 15 bar. Okay, so as I said, we're looking Hg. Okay, so Hg is here, this column. Okay, this column up to 15 bar is here. Okay, so that's 2792. So the final one, I think I already explained that in the announcement. So when we're talking about the change in specific internal energy, so that's delta lowercase u, okay, specific internal energy delta u. So during condensation from saturated steam to saturated water, so when anytime we're talking about the change, we're going to always use the end state to subtract the initial state. So in this case, end state is water. Okay, so water, as I said, we have a subscript F, saturated steam, so that's G. Okay, and the delta U is always use end state, so that's 2. Okay, 2 saturated water, so that's end state is UF, subtract UG. Okay, so that's the correct equation we're going to use, so according to the pressure of 3 bar. Okay, and then if you check, so that's pressure 3 bar is here. Okay, and we're looking at the U's, so UF, UG. So we have 2 values here, but need to be careful. We're using UF subtract UG. Okay, so we use a smaller number subtract a big number, and this will give you us a negative value. So it's minus 183. Okay, so it should be negative value for that. Okay, so now we're going to move to question 4. Question 4 and question 5, actually they're using the same figures here. Okay, so in question 4, we need to determine the initial specific internal energy U1. So 1 is here. Okay, because this is a dome shape, if anything under this shape, so this means that 1 is a wet vapor, and only wet vapor has got a dryness fraction. So initial state 1, the dryness fraction x. Okay, so we're going to use a formula sheet, which is only actually, okay, one set of equations here to describe a wet vapor, wet steam. Okay, so we're going to use that because U1 is U wet. Okay, because at the state of 1, that's a wet vapor. State of 1, wet vapor, we're going to use that equation. So here, I'm just going to write on this paper. So U1 is equal to U wet x times UG plus UF. Okay, so we just need to find out UF and the UG according to that pressure. P is equal to 10 bar. So in this case, we're going to use that from steam table again. So that's saturated. Okay, so we'll only use saturated water and the steam table to find out UF, UGs, because you can see there's UF, UGs here. So at 10 bar, so UF 762 and UG 2584. Okay, so just to put all the values inside this equation. X 0.85 times UG 2584 add, so that's 0.15, so 1 minus 8.85 UF is 762. So this will give us answer okay, that's just for U1. Okay, initial specific internal energy U1. So that's U1. Okay, so let's move to the final question. Using the initial specific internal energy U1 calculated here, determine the amount of heat transfer. So we need to calculate the Q. Okay, during this process, assuming the work done, so the work done is 620 kilojoule. Okay, so Q, W has been given. Okay, so again you can see that this is a you can see this is a closed system. As I said, in closed system we only have that one equation to describe the relationship between Q and the W. Okay, it's equal to U2 subtract U1, right? You can see that actually all the U numbers we checked, we found from the specific table or from the steam table. You can see all these values are all specific values. Okay, they're all in the lowercase, so which means that we have to use M mass. Okay, just lowercase U2 subtract U1, right? So we just found actually we found the U1. Okay, so U1 has been given. So what we need to do is find out the U2 first of all. So let's have a look at the 2, state 2 on this diagram. Okay, 2 is not within under that region. So 2 is beyond this red line. Red line means that number 2 is actually superheated. Okay, so this is superheated state, and to find out specific internal energy for state 2, we have to use the steam table again, but we're not going to use that saturated water in the steam, so we have to find out the superheated. So now this is superheated steam. Okay, so the pressure, so again is still 10 bar, and also how about pressure? So the pressure for state 2 is 350, so that's 10 bar. Okay, 10 bar, so we have all these 9 10 bar, and we need to find the temperature as well, 350. So that's the column, and then okay, so this is a group of data. Okay, so these don't use that because these are all with a subscript of G, which indicates these are the saturated steam. Okay, so these are overheated, superheated steam. Okay, so here we have a group of 4 data here. The first one, V, U, H, S. So we're looking at the U, so that's second. Second is here, is 2875. Okay, I just wrote here U2 is 272875. That's for superheated steam. And now we just can calculate the final answer for Q. We move W because W has been given. Add M. Where's mass is here, 2.5 kilogram times U2. U2 we just found out. U1 is here. So then we can calculate the final answer. Okay, so that's the final answer for the heat transfer. Right. Okay, these are all the 5 questions in quiz 2.